This is taught by Boldrin, and the title is A Time Problem in Perturbation Theory. Please. There you go.
So the title of my talk is The Time Problem Perturbation Theory, and it's based on this paper, which I guess you cannot really see here, but which was published earlier this year. And the outline of my talk will be, first I will give you an idea of what we mean by time problem in physics. Then we will discuss what the reduction formalism is. And then we will see how we can do some clock transformation as well as what a clock is. And then we will discuss the canonical model of primordial spacetimes. And then we will move forward to quantization and semi-classical approximation. And after that, we can actually see our results. And after our results, we can actually, I will just give you the conclusion. So what we got with our results. So time problem in physics. So there are many different approach, many different meaning that people give to this. Our idea is that GR is a diffeomorphism invariant. So the choice of internal time variables has no physical consequence. So we can actually choose whatever time we want, and the physical meaning of our theory doesn't change. However, when we go to a quantum theory, the different choice of time actually produce a unitarily inequivalent quantum model. So we have a problem if we want to unify the two theories. So the problem of finding the correct interpretation of these non-equivalent models is commonly known as the time problem. Isham, actually, in this paper here, he gives a more technical interpretation, which is the prime source of the problem of time in quantum gravity is the invariance of classical general relativity under the group diff-M of diffeomorphism of the space-time for manifold M. This tends against the simple Newtonian picture of a fixed time parameter and tends to produce quantization schemes that apparently lack any fundamental notion of time at all. And what we are interested in here is the last part, this here, in which you say, from this perspective, the heart of the problem is contained in the following questions. So the questions I'm going to show you now, we use them as a test for our paper. So we found them afterward, but I think it's nice to have some kind of way to test if what you find can actually be consistent with the question that he posed. So the first question is, how should the notion of time be reintroduced into the quantum theory of gravity? Then he asks, should attempts to identify time be made at the classical level, i.e. before quantization, or should the theory be quantized first? And then he asks, can time still be regarded as a fundamental concept in a quantum theory of gravity, or is its status purely phenomenological? And lastly, the last question he posed is, if time is only an approximate concept, how reliable is the rest of the quantum mechanical formalism in those regimes where the normal notion of time is not applicable, and how can we relate the notion of time with the notion of probability? So at the end of my talk, in the conclusions, I will try to give some answers to this question based on what we did in our paper. Now we go to the more technical part, and I will now introduce you to the reduction formalism. So we know that the Hamiltonian constraint is a consequence of the fact that the dynamics of free surface is generated by infinitesimal time-like diffeomorphism, and later leave the full four-dimensional space-time invariant. The Hamiltonian constraint dynamics is something that is a feature of all canonical relativistic theories, being it Einstein gravity or modified gravity. So we know that we have this Hamiltonian constraint. Moreover, we have that the canonical relativity assumes the lack of an absolute external time in which three surfaces evolve and replaces with internal variables that serves as clock. So every time now I'm going to talk about clock, that's what we mean, and in which the dynamics of the surface takes place. So what we have now, we assume we have this n+1 set of canonical variables, and so the usual pair, we have Q and P. And then we have our Hamiltonian constraint that we call C in this case. And the Hamiltonian constraint, of course, is a function of our canonical variables Q and P. And since it's a constraint, it's considered to be weakly zero. So this wiggly lines is a weak equality and is using Dirac notation. And it means that it's zero on the constraint surface. And then what we can do is, if we have a variable, in this case we call it Q0, such that the Poisson bracket with the constraint is different from zero, then we can define this Q0 as our internal clock. The reason why we can do that is because being different from zero, it means that it's either greater than zero or smaller than zero. So it means that it's monotonic variable. So its dynamic is monotonic. That is what we want for a time, either go forward or backward. So this is what we're going to consider as our internal clock, Q0. Okay, from now on, just in this part of the talk, I will use, instead of Q0, you will see I will use T. But what we have now is that now that we consider a new time, we have to actually reduce, we call it reduced Hamiltonian formalism, and we have to write our the symplectic form, in this case is dq wedge dp, but we have to write it with our new internal time. So the symplectic form in the constraint surface, so this annotation, now it's going to be written in this way, where dt again is just a new notation for dq0. So this is our new symplectic form with our new internal time. And where h, in this case, the non-vanishing reduced Hamiltonian, which is the function of Q0 and Qi pi. So where I now goes from 1 to n. And then we have that P0 plus H is weakly zero. So now that Q0 and P0 are removed from our phase space, the remaining dynamical variables are no longer constrained. So usually it's said that we solve the constraint in this case, and our new dynamics now can be written in terms of our new time here. And now the dynamics is just related to these non-constraints variables, so with I that runs from 1 to n. And we again, it's computed with this H that I showed you before. Okay, so now that we reduced our formalism, we want to see how can we actually change clock in this formalism. Okay, so to change clock, it just means that we saw earlier from the introduction that we can choose whatever clock we want. So we can take in this case just tilde t, and it's going to be a function of our canonical variables, so the non-constraint one, and the time, the time we have previously, so t. So this monotonically, as I said before, we have to choose t tilde again, as it says that it varies monotonically, and again it must satisfy this condition here, which means if you actually write it explicitly, that this is the condition that it must satisfy, where this here is just a Poisson bracket between t tilde and h. Okay, so again, as before, we have to write our symplectic form. So now it's going to be in terms of our tilde variable, because we choose another reference frame. So the problem is that we have these variables here, which are the new one, the tilde one, and we want an invertible map between the old variables and the new one, because we want to be able to change variables as we wish. So the question that we must ask is, are those transformations canonical? And the problem is that usually they are not canonical. So generally, they are non-canonical transformation, which canonically transforms. So clock transformations form a group of generally non-canonical transformations with canonical transformation as its normal group. So what we have is that if a dynamical system is integrable, then we might find a complete set of canonical constants of motion, which we define as di, where I is the same as before, so from 1 to n, which are a function of qj, pj, t, so the non-constraint variables that we showed before, and our time. So those variables are usually called Dirac observables, and they're usually found when we work with constraint systems. So they were. Okay, so now we will see what fundamental role these variables have for our in our paper. Okay, so we have the new canonical formulas based on the new internal clock. So those are our new variables, and you see now we switch to work with our Dirac observables. And one important feature, really important, is the fact that the Dirac observables, you see, di, their form does not change if you write them in terms of our untilted variables or as a function of the tilted variables. So the formal description of the system is the same in all clocks, only the physical meaning of the clocks and basic variables change. So this is a really fundamental part, and we will see how it's going to play. So now we have two clocks. We have t, which gives us these variables, and then we have t tilde, which gives us, of course, the tilde variables. So now we will consider the canonical cosmological model, and what we have, so what we consider as our background, the foundation in which we work on. So we consider, for simplicity, a flat Friedman universe filled with radiation. So we have W is equal to 1/3 and perturbed by gravitational waves. So we have that our line element is given by this. And so we have that HIJs are our tensor perturbations, so our gravitational waves. And they satisfy the usual conditions. So we have that they must be traceless and transverse. So we have now a set of background variables and a set of perturbed variables. So we have that the background variables will now be given by our scale factor A and the conjugate momenta PA. And as perturbation, we identify this variable mu, which is just a rescaling on our H, which I showed you before. So it's AH. And then we have the conjugate momenta here, pi. And this is just the polarization of our waves. Okay, so now we have that our second order Hamiltonian constraints, so the sum of the orders up to second order, is given by the background plus our perturbed Hamiltonian. So the background Hamiltonian here is given by this, so the usual one is minus 1/2 PA squared minus P0, where this P0 is related to our radiation fluid. And however, if we actually consider Q0 to be eta, so our conformal time now, we have that our Hamiltonian can actually be rewritten more simply in this form. So where 0 again stands for the background, it's just change of notation. And so it can just be written as 1/2 PA squared. And this is what we call the physical background Hamiltonian. For the perturbed part instead, so for the perturbed Hamiltonian, what we have is that it's at the second order, and it's going to be a sum, minus the sum over the polarization, so this. And in particular, this can be written as, so those are just the conjugate momenta, so is the usual form, and we have k squared minus, this is the derivative with respect to the conformal time, and this is our potential. And so this is our perturbed Hamiltonian. So we saw before that if we set our if we want to change clock, we also need to find our canonical pair of variables, and we saw before that those are called Dirac observables. So now we will see that they are non-dynamical. So as before, so the derivative with respect to eta satisfy this equation, and it must be equal to 0, and it's equal to 0. So by using this equation, by solving this equation, considering as Poisson bracket both given the Poisson bracket given both, of course, as a function of the background variables and the perturbed variables, we can actually find a form for the 0th order Dirac observables and 1st order Dirac observables. So for the 0th order, we have that D1 is given by this simple form, so A minus PA eta, and D2 is simply PA. So again, we just found this by solving these equations at the 0th order, so we don't consider the second order here. And at 1st order of perturbation, what we have is that we have to solve this equation, which seems complicated, but we can find that a solution is of the type of this. of this equation. So we have mu k, alpha as a function of y, plus pi k and times beta as a function of y, where y is actually eta plus a over pa. So if you plug this inside of this equation, what we find is we can find 4 first-order constraints, which are in these two different forms, and they're given by these equations here. So those are our Dirac observables at the background, and previously we saw the one, at the first order perturbation, we saw the one at the background. Okay, so both set of Dirac observables that we find, they form canonical pairs, so they satisfy the usual relations, and so the Poisson bracket between the background one is 1, and at first order just delta lambda lambda bar. Okay, so now we want to try and see what happens if we actually make a general clock transformation. So a general clock transformations look like this in our case. So we go from eta to eta tilde, but in this case, eta tilde, we define it as eta plus delta, where delta is what we call the delay function. Okay, so we saw before that our background level Dirac observables are given by this equation here. So I saw you before what they were, but as I told you before that this was the most important part, because now what we can do is actually, by equating these two formulation for the untilde and tilde variables, we can actually find our tilde background variables. So a tilde and p tilde. So we see that a changed and now it's a function of our delay function, but p remains the same. And then we can do the same for the first order. So again, we use the fact that the formulation of the Dirac observables does not change based on the coordinates that we used. And what we found is this interesting equation here that basically tell us that they are just a rotation of the other. So the tilde perturbed variables are just a rotation of the untilded one. Okay, so and those are what is going to be important in our case, and we'll see for our results how we'll use them. So the clock transformations, as we see, modify temporal relationship between events. And what it means is that in some case, the events, if in some frame, for example, in the untilded one, some events are contemporary, simultaneous, they can be not simultaneous anymore in the tilted frame. However, they do preserve the evolution of cosmological space-time consisting of homogeneous spatial leaves with small perturbations. So it means that the lapse function does not change; it still goes forward. So we preserve the informalism, let's say, and this is the formulation of the n tilde, so the tilde lapse. Where for this formulation, however, we assumed that the delay function is not a function of time itself. So now I will give you more an idea of what this delay function here is, because it's not it's general, but with some constraint. And in particular, the condition that this delay function must satisfy are that the new clock must run forward. So as we said before, usually a clock is a monotonical variable. So the dynamic of the variable is monotonic. And it means that the eta tilde over d eta must be, in this case, we chose it to be greater than 0. And then what we have to consider is that the ranges of the basic variables must be preserved. And this is a condition more also for the quantization, actually. What we have is that in this case, we have that this condition is trivial because, as we saw, PA is actually equal to P tilde A. And then what we have is that this condition is not trivial, and the delay function, it means that the delay function at vanishing scale factor, so delta for A0, must also vanish. And also it means that it's irrelevant, as I said, it's irrelevant in the classical case, but it's crucial for the existence of a bounce at the quantum level, because it allows to actually unify the contraction and expansion, and not move our border, let's say. Okay, so now we can go to the quantization, because we saw how it works at the classical level, so we can see what we have now at the quantization and semi-classical approximation. Okay, so working at the background, we have that we work in the positive half line, so a bigger than 0, and we have that p is not self-adjoint. So it means that we have to introduce a new operator, which is usually the dilation operator, which is defined in this way. And if we expand this, we can actually find our semi-classical background Hamiltonian, which is in this form, where K here depends on the ordering. And what we have is that H is self-adjoint for K bigger than 3 or 4. So that's what can be found. Okay, so now to get our semi-classical Hamiltonian, we have to compute the expectation value of H0 that I showed you in the previous slide, where these states, they are actually given by this formulation, so they are coherent state, where Xi here is such that the expectation value of Q and P computed with this state are respectively A eta and P eta. Okay, so now we have our new Hamilton equations, which are defined in terms of this Hamiltonian, semi-classical Hamiltonian. And then we have that we can write the semi-classical Hamiltonian. So if we compute the expectation value I showed you before, it's now given in this formulation where this K, here Gothic K, is again greater than 0 and whose value is related to the one in the that we saw here, to the value of K that we saw for H hat 0. Okay, so okay, now if we solve this equation, actually, the Hamilton equations, we can find the solutions. And what we see is that now the solution for A, there is no solution for A eta equal to 0. So it means that we avoided the singularity at the quantum level with this formula, which is what we want to introduce in a bounce. Okay, so now we have the background evolution. If we compute our A eta in P eta, is given by this equation here. And then the semi-classical potential, so A prime prime over A, as I showed you before in the Hamiltonian, is actually given by this formula. And this, it's the plot of the potential. As you see, it does not go to 0 unless for at the classical limit. So we avoid the singularity. And now we can actually focus on the perturbation. So we see at the background how it works, so what our variables are. And at the perturbation level, if you remember, we have mu and pi, and now we can just write the operator correspondence, which are a function of A and A dagger. And A dagger, they of course satisfy the usual commutation relation. And then we have the equation of motion in the Heisenberg picture, which are given by this formulation here. And then the modes satisfy the following equation. So we find this equation, a secondary equation, which using the semi-classical potential that we saw before, we can actually write in this way. So this can actually be integrated numerically. And this is what we did for our in our paper. And it can be done, of course, if we set some initial conditions. So our initial conditions are that in the far contracting branch, so where eta is eta initial, so smaller than 0, and for the semi-classical potential of eta initial to be really a lot smaller than k squared, and we have no gravitational waves, that the field was in a vacuum state, so before the bounce, basically. And then we have that our initial condition for mu and mu prime are given by these two equations here. So we found our coefficient, our variables for the background, and we found our the equation that we want to solve numerically for the perturbation here. So as we saw before at the classical level, when we change clock, what we have is that A and P, they change with the transformation is given by these equations. And then for the perturbation, we have this rotation. And this is basically what we're going to use now in the results. So basically what we did is that we compared our result in the new clock and in the old clock, both for the background and the perturbation here. Okay, so now we can look at the result and what we obtained. So first, before looking at the result of the background and the perturbation, I will show you an interesting thing that we have using this delay function. So as a delay function, I showed you before that you basically have to, it has to satisfy two things. One, it has to be the time must still be monotonic. And then what we have is that it has to satisfy some boundaries. So we found that this, as a family of delay function, it works. And in our paper, actually, we use another delay family too. We showed another family too, which works. But in this presentation, I'm only going to show you this one, where A, B, C, D, and E, so all the capital letters here, they are just coefficients that we changed. So what we see here is that if we plot eta tilde as a function of eta, we find that the time is not monotonic anymore. But this is a feature that is only present at the quantum level. So in this case, this new clock, they are not monotonic anymore. And these different delay functions, delta 1, 2, and 3, are just values of this delta for different coefficients. And those deltas that you see here are the one we're going to see throughout the other results now. Okay, so at the background level, what we have, I showed before that those are the semi-classical value of the background, variables. So if we plot them compared to our new clock, you can see this interesting thing. So the black line here, the full line, is actually our variables computed with eta. So let's say the initial clock, and all the dotted or these different colors trajectories here, they're for different clocks. So what you can see here is that the difference in the trajectories is only present around the bounds. So when you go to the classical limit here, so for a really big scale factor here, there is no discrepancy because all the trajectories, they unified here. And this is what we found to be really interesting, because it seems that in this formalism, the only problem that we have, so the only discrepancy due to the change of clock at the semi-classical approximation, is only around the bounds. So when the quantum regime is actually dominating. And the same we find actually for the perturbation. So for the perturbation, we find that you see here, so it's not visible in the full plot, but we have some zoom here. So we have different wavelength here, so 0.1 and 0.5. And you can see still here that they converge really early here. So around here, they already converge. So in fact, you cannot see discrepancy in these plots unless I zoom in. And so again, it's again around eta initially is equal to 0. So more or less, so when we have the bounds. In particular, you can see this in this plot, we use different wavelengths, different k. So a really small one, like k equal to 0.01 or up to k equals 0.5. So you can see the different behaviors of the clock, so when they converge. And you see that delay of the convergence due to the different choice of delay function. So as you can see, for example, in this case, for k equal to 0.5, they are converging around here. So let's say around 1.5, let's say. But here they're converging a bit later in the clock. And also the effect of the clock is a bit different based on the k we have, because the deltas, they are always the same around for all these trajectories. So this means that the larger the wavelength of the perturbation, the larger the relative clock effect, and the longer it lasts in units of its oscillation period, but still they converge at some point. So another plot that gives out quite an interesting idea is this. So in this case, we have the initial state here. So we are plotting the imaginary part of mu, because here I didn't explicitly say that, but this is the real part of mu tilde. And in this case, we're plotting the real part of mu tilde as a function of the imaginary part of mu tilde. So what we have here is that this is the initial state. And then after the bounce, so it goes like, it's like moving in this way, basically. After the bounce, we see that we have a squeeze state. But still, the clock effect, so the effect of changing clock, is only visible around the bound. So when we go from one initial state to a current state to a squeezed one. And this just, you can see only for k equal to 0.5, just because the plot is better, but this effect is consistent with all the other wavelength, with other k that we used. And I didn't say that before, but we used a bounce parameter equal to 1, and also omega was equal to 1 throughout all these plots, but we tried with different coefficient, and it was the effect is always the same, so that we have only the predominant effect is only at the bounce around the bounce run, but not when we go to the classical limit. So now for the conclusion, we can actually try to answer Aisham's questions. So how should the notion of time be reintroduced into the quantum theory of gravity? So for our work, so in our paper, we have that our approach relies on evolving internal variables called clocks, and we express the dynamics of the dynamical variables in terms of this clock. So that's what we did, and that's how we found that in the classical limit, this clock problem, it's not there, even though we are still using same classical trajectories. And then should attempts to identify time be made at the classical level or after quantization? So in this case, as I showed you before in this talk, we first reduced the Hamiltonian formalism based on a selected clock. Next, we quantized the reduced formalism, as in the clock was an external and absolute time. However, this is neither external nor absolute. And the instantaneous value of the clock determines the instantaneous physical state of the system. So switching to another clock entails a change in the physical interpretation of the clock and the entire state of the system. So we cannot say like what happened if you change the clock afterwards, but you saw that the clock, they became non-monotonical still at the quantum level. But in our case, so the answer to this question is that we did it at the classical level. Okay, so, and now can time still be regarded as a fundamental concept in quantum theory of gravity? So the answer is that no. And the reason is that in our approach, there is no fundamental time. The fundamental concept is change or evolution. So I talked about the evolution of this trajectory that we have, and meaning that we merely need to assume that the 3+1 split of the underlying geometry imposes an ordered set of hypersurfaces. So the clock serves a tool to deriving the predictions. So once a class of clocks converges to a unique dynamics, any one of them can be treated analogously and deserve to be the quantification of time. And any quantum dynamical variables become described in them by unique Schrödinger equation. So there is, we lose this absolute time concept that we usually have. And then, so this is a question that we didn't tackle directly. It's possible to do it with our approach. So it asks if time is only an approximate concept. So how reliable is the rest of the quantum mechanics formalism in this regime, or the normal notion of time is not applicable. And we say that the quantum mechanical description in the regime where different clocks exhibit different dynamics is an essential part of our theory. So it describes the deterministic evolution of the system. However, this regime does not seem to allow for any mechanically meaningful dynamical interpretation in terms of relational change. So the idea is that this question can actually be answered with our approach, but we didn't actually directly try to answer this. So I think this is an interesting thing that we can do in the future. And lastly, so to conclude with our work, what we have is that setting well-motivated initial conditions in the classical puzzle, as we did and I'll show you, one gets an ambiguously physical prediction for the classical future in which we happen to perform the measurement. So with classical future, we mean big scale factor, as you saw in the plots. And in other words, we have shown that the lack of predictability in the quantum regime does not exclude the fact that the theory permits meaningful physical prediction that can be tested with observations. So that's what we found with our results. So thank you for your attention.
Questions? Comments? Remarks? If not, take us.
I have a question, because you found that outside of the bounds, the dynamics independently of the choice of the clock is the same.
Yes. So what I was saying is that, so in this plot, so let's take this because this is the one in which we can see it better, but it's the same for the perturbation. So when I was talking about the bounce, so we are here, right? So you see it's around 1, because that's what we chose. So the time, so those are the trajectories of our background variables, right? So you see that the trajectories, they are not convergent, they are not the same around the bounce, right? But you can see, so the plot stops at 4, but if you go for bigger A is the same, I assure you, because it was, we can do that. They actually converge. So what we have is that there is no, you can see that there is no change in the trajectories for a big scale factor. So that's what I was saying.
Any questions? Okay.